Okay, so we've literally covered half the chapter, and that's all about doing confidence interval and doing a inference test on a difference between two proportions. Okay, now we're going to do the same thing on a difference between two means. And this is just like dealing with proportion, only now we're going to obviously use a t-distribution because it's a mean. Um, this one you will actually be able to see both of your sets individually, not like last chapter when we did the mean of a difference where we subtracted first. Okay, so we're going to be comparing two means in two different samples and doing the same thing. Okay, so we need to look at the sampling distribution, and again, you should know this. This, I'm sure, like I said, is probably becoming part of your nightmares. We need to understand a couple things about the sampling distribution, and this is where we get the formula for like the standard deviation and stuff. Okay, so biggest thing. Okay, we already know that if both of the distributions, both of the populations are normal, then the sampling distributions are going to be normal, just like always. Okay, so we don't have to worry about that part. If the population distributions are not normal, right, we have a couple of rules. We have to take a large enough sample size, right? That's our n greater than or equal to 30. And then if we take that large enough sample size, then your sampling distributions are going to be approximately normal no matter what. Now, if we end up with samples that are less than 30, you're going to have to graph them. You're going to have to do a histogram to prove that they are normal enough to work with. Okay, that's part of our conditions. Okay, so this is just the same thing that we've been saying since chapter 7 when we did sampling distributions, right? The central limit theorem, where you have to take a sample greater than 30. Okay, so the center of the sampling distribution, we know this, right? That was our normal one sample basically, or one population thing. Okay, so, and our standard deviation, as long as we took less than 10% of the population, right? So now we are looking at the difference between two means. This was our normal stuff for one sample basically. Okay, so now if we're looking at two different samples, right, to compare, okay, we can just go ahead and subtract the means. We know that because means are one of those things that you can go ahead and just subtract, right? But we know this, we cannot subtract standard deviations because they're square roots, right? Okay, so we have to do the same thing that we talked about before. We basically have to get them back to the variance, add them together, and then take the square root. Okay, so what does that mean for you as far as your formula? Okay, it means you're going to have another big square root and that you're going to have to square some things inside of it. Okay? We have the variances, that's the standard deviation squared, divided by their sample sizes, and then take the square root. Okay? What does that look like? It looks like that. Okay? So, whatever standard deviation they give you, right? And normally what we would have done, that, right? That would be the standard deviation of the sample, and we would divide it by the square root of the sample size. Okay, so we can't just add two of those together because they have the square roots in them. So this is what happens. And this actually is on your formula sheet, right up underneath the difference of two proportions as far as the standard deviation. It's the difference of two means. Okay, so we're going to have to square the standard deviations that they give us, put them over their individual sample sizes, and add them together all up underneath the square root. Okay? So it's not bad. It's just a little bit more complicated as far as the square root. But other than that, nothing really changes. We've been doing inference tests for a while. We've been doing confidence intervals for a little bit of a while. This should be becoming second nature to you as far as how to do it. Okay, so let's do some practice ones to make sure we're good. We're going to do this just like we did with proportions. We're going to do a basic probability question first, just so that you can show, because these tends to be open response questions too, where you can show that you understand how the differences combine together. Okay, so heights of 10-year-old girls are normally distributed. There's your first mean and your first standard deviation. That's messy. Okay, so first mean, first standard deviation. So we're going to call that x bar 1 and sigma 1, or s of x1. All right, 10-year-old boys normally distributed, mean, standard deviation. Okay, we're going to take a simple random sample of 12 girls and 8 boys, so that's 20 total, right? Okay. What could we say about the mean, the difference of the means? Okay, so the sampling distribution is shaped normally because the populations are normal, and that takes care of the fact that our sample size isn't bigger than 30 for both the girls and the boys. Okay, the center of that distribution of those differences, okay, is going to be the girls' mean, because they are subtracting females minus males, the girls' mean minus the boys' mean, and that's going to be 30.7, I think. Yeah, 0.7. Okay, so the spread of the distribution, and this is going to get a little bit bigger as far as how this goes. Ready? You take each standard deviation, square it, put it over its sample size, and then put the whole thing in a square root. Okay, so 2.7 squared over 12 girls, plus 3.8 squared over 8, added together all inside the big square root together. Okay, and that's going to equal 1.55. So we have our mean, right? That's our x of f minus x of m. That's the difference between our two means. There's the center of our distribution. There's the standard deviation. So let's do an actual question from it. Okay? Same information, but you always have to get the mean and the standard deviation first. Okay, what is the probability that the difference between the means is less than 0? Okay, so as a probability question, and again, that is the probability that it's less than 0. Okay, that's the statistic that I'm checking, whereas this is the parameter, right, that I'm working with. Okay, so this is what I'm wanting to check, and that's my piece. So 0 minus 0.7 divided by 1.55. Okay, and it's going to be a negative, and that's fine because, it's just a normal probability question anyway. Now, here's the question. Are we using T or are we using Z for this? Well, let's take a look. Is that the population standard deviation right there? Is that the population standard deviation? Yes, it absolutely is. So in this one instance, that's the one we talked about before, about this being allowed to use a Z rather than a T. Okay, so what is divided by 1.55? Should be negative 0.45. Okay, and so we're looking for a Z-score of less than negative 0.45. Right, and if you're being given probability questions like this, normally they're going to go ahead and give you all the information, so you have the population standard deviation, go ahead and use Z. But that's one of those things that you have to study and you have to remember. Okay, so go ahead and look up that Z-score. Okay, so negative 0.45, you should have gotten 0.3264. So move that down a little bit so I can actually deal with it. So 0.3264. So again, if we're going to put that in words, that is a 32.64% chance or probability of, well, what does it say? Of difference between girls and boys' height is less than 0. Okay, now if I'm subtracting girls minus boys at that age, because that age is like 10 years old, what does that mean? If I'm subtracting girls minus boys and you're getting answer less than 0. Right, there is a 32.64% chance that at age 10, a boy will be taller. And that's what that means in like context or in reality for it. It basically means that he has a 32% chance, any given boy has a almost 33% chance of being taller than an average girl at the age of 10. Okay? That's basically all that means. All right, and this is just an exercise to make sure that you can do this part, because that's really how we do an inference test, that you can find your standard deviation and you can find your mean. That's all it is. We're just doing practice on that. All right, so let's take a look. And we're going to actually run the data on that one. We're going to run a ho-ha. Okay? And in order to run a ho-ha, let's make sure I have what I want. Yeah, this is what it is. That's basically the overall formula. Okay? This is still statistic minus parameter divided by the standard deviation of your statistic. Okay, so that hasn't changed. And if we're doing a ho-ha test, right, 99% of the time what they're going to tell us is that the difference between them is 0. Right? So it's just going to be your sample subtracted minus 0 equals, over the standard deviation. So this is normally equal to 0. Okay? So we're going to run a ho-ha on this. Right, this is your yeah. Okay, that's usually the case, and actually I think this is backwards. It's not supposed to be x1 minus x2 is 0. It should be mu1 minus mu2. We assume the parameter is 0. Okay, so if we're dealing with means and not proportions, and you're not given your population standard deviations, we're going to use t-scores, right? And for those, we need to have a degree of freedom. Okay, that's one of the big things with t-scores, is that you are using your t-table. You have to have your degrees of freedom. It's not a big deal, right? We normally just, oh, it's one less than the sample size. Ooh, what if our sample sizes are different? Well, it's kind of like the same thing if you had a number that was not on the table and you went for one less and you had to like go further down. Okay, so like, let's see, for your degrees of freedom, let's say you had 35 in your sample size, right? And 34 is not on our table, so you would go down to 30, which is the next closest one down. It's very, very similar to that. You're going to use the smaller of the two samples, and that's going to be your degrees of freedom. So if you have a sample size of 40 and a sample size of 50, then you're going to use 40 for your degrees of freedom, okay? Or 39, rather. All right, so if you have two different sizes. All right, so let's go ahead and run this one, and then we will be done for today. Okay, so we got girls and boys. We're going to run a significance test. We're trying to prove that girls are taller than boys at the age of 10. Okay? Our null is not going to change. Our null is still based on that we assume that there's no difference, right? And here's the thing. We're not going to write this out as 1 mu here and define it, okay? Please make sure that you are stating mu1 minus mu2. You could also write mu m or f or g or whatever it is minus mu b for boys, so equals 0, okay? And then if we're going to make this the girls and we're going to subtract them, if they're taller, then mu1 minus mu2 would be greater than 0. Okay? And they've already told us what the alpha is. I'm just going to write that down to remind me. Okay, so what is this? Mu1 is the true mean height of girls at age 10, right? And mu2 is the true mean height of boys at age 10. Okay, so we've defined our variables. Okay, now I know some of you are probably wondering, can I go ahead and combine them into one statement? Yeah, it's just got to be written very specifically. Mu1 minus mu2 is the true difference. You have to put the word difference first, because right, it's not the mean of a difference, it's the difference of means. So you'd have to put the word difference in front of the word mean this time. Is the true difference in the mean heights of girls and boys at age 10. Okay, so yes, you could put that in a one specific statement. You just need to make sure that you put true difference in means instead of the true mean difference. This is what we kept saying before. True difference in means. Okay, so random. I do believe they said in the other paper or on the other page that it was an SRS. Okay, normal. Yes, because our population is normal. So we don't need to worry about sample size. Independent. Okay, there are more than 12 times 10 girls and 8 times 10 boys. And I don't even think it said where, so it's basically in the world. Okay? So we're good. We've done this before. So we're going to set this up. Okay, and we're going to write it out to make sure we've got it. We're going to have 7 degrees of freedom. That's one less than the smallest group. Okay, so we already knew that our piece was 0.7. Okay, in this case, our parameter is 0 because that's what we said the null was. All right, and we already knew that the standard deviation combined was 1.55. The only thing that this is going to change, and it's really not going to change much because we're doing a greater than 0, is instead of getting a negative answer, we're going to get a positive answer this time, which was like 0.45, I think. Right? 0.45? Yeah, 0.45. Oh, good. Okay, so with 7 degrees of freedom and your probability or your t equaling 0.45. So you need to go find out what p-value is closest to a t-value of 0.45 at 7 degrees of freedom. And I'm going to look at this on my table. You should have this table in front of you. Okay. Okay, fairly close to the left-hand side. And it's somewhere between the 0, 0, 0, 0 and 0.711 as far as our values. And the p-values that it's between is between, if I can get this, 0.25 and 0.50. Okay, so both of those are greater than alpha equaling 0.05. Okay, so conclude, okay, we are going to fail to reject, and we do not have enough evidence to conclude that at age 10, girls are taller than boys. I mean, that's really what we are being asked to find, right? And this really doesn't, it's not really surprising, being that the boys have a 30% chance of being taller than the girls. Okay, so that means that, I mean, what we're saying basically is that the girls are like always taller than the boys. We don't have enough evidence to conclude that. That means sometimes the girls are taller, sometimes the boys are taller, sometimes they're equal. Okay, and sometimes there really is no difference between them. And so we don't have enough evidence to conclude that at age 10, girls are taller than boys. Okay, so we are done for today. Send me remind questions if you are stuck on anything. You should be continuing to read section 2. You should be continuing to work on the problems from your textbook from section 1. I will be giving you some more tomorrow to work on, plus some open response practice. Please, keep a special eye on the vocabulary, because that's where y'all were struggling. And take it easy. I'll talk to you tomorrow.